So omega n has uniform contact support in space for all t. So you have a bound on omega n in LP, uniform in M. Finite speed of propagation coming from this, because you are transported by this velocity. So not only finite, but independent of M. So this constant in the end, and when you go from L infinity to LP, it will be bounded uniformly.
What is going to grow at time of infinity?
It grows. It can grow, sure. So what can we do now with these LP bounds? We see that in L infinity we cannot have a control of the gradient, but is it better in LP? The answer is yes. The answer is yes. You can see it for p equal 2. I mean, for p equal 2, you can use Fourier, and you will see that convolution, of course, becomes a product. So u hat of n will be k hat of psi times omega n hat of t and psi. Right. And k hat, you can compute, and you will see it's homogeneous of degree 0. It's bounded, and sorry, this is the gradient of k, which is involved here. Gradient of the Buan-Savart canon. So this is homogeneous of degree 0 because gradient of k is homogeneous of degree minus 2. And it's bounded, so you can use Plancherel formula to see that for any t, the L2 norm in space will be bounded by the L2 norm of omega n of t. So this will be bounded. And this is the gradient. And this is the... So I can add gradient everywhere. Because I'm interested in the gradient. You can add gradients here and there. So you see that things go right in L2. And more generally, when you look at the convolution with gradient of k, of course it's not a convolution with an L1 function, but it fits into the framework of what is called singular integrals. Okay, so for functions like this, like gradient of k, which are almost in L1, and which have some additional good properties, everything everything works fine in L2, but everything more generally works fine in LP, or P strictly between 1 and infinity. Okay, so if you want, I mean, this is a big theory, so if you want some information, you can Google singular integrals, you can Google Herman-Niki's theorem. And the main thing is that for P strictly between 1 and infinity, the gradient of un in LP will be bounded by some constant depending on P times omega n in LP. Okay? I mean, put the prime here. This is not the same constant as before. So this will be bounded overall for any time. So here we do not use it because we are happy with the case P equals 2. Okay? But it will be useful in performance.
But CP actually grows.
Yes, yes, it grows in time, sorry. So that's a CP of t, sorry. It's a CP of t here. Yes. I mean, for compactness, I mean, for existence or uniqueness, you can restrict to some finite arbitrary time. So it's really no big deal. But you're right that here I should put the t. But this is independent of f. That's the main one. Okay. So you see that we can recover bounds on the gradient of un. So we have uniform in n bounds on the gradient of un. From the equation, okay, then we can perform some convergence argument because we have this uniform bound on the space derivatives. We have uniform bounds on space derivatives. Then I don't have time to detail, but using the equation, we can obtain uniform bounds on dt un. So these uniform bounds will be weak, which means you will, when you are familiar with this kind of arguments, you have bounds on the hard part is to get bounds on the space derivatives, and then you just use the equation to get bounds on time derivatives with values. These bounds are rendered in some weak space. So for example, in a Sobolev space with negative index. Okay. I don't have time to detail, but the general idea is that you have uniform space bounds, uniform time bounds on derivatives, and so there is some kind of Ascoli-like theorem which will allow to get compactness of un. Okay? So thanks to a variation of Ascoli's theorem, which is called the Aubin-Lyons theorem, what you get is compactness. Sorry? This is exactly, this is the problem. This is an old, now pretty old theorem. So, thanks to this theorem, you have to believe me, there is compactness. You get compactness of the sequence UN in, say, L2 log, space and time. For the strong topology. Okay? So you will find some subsequence of UN that converges strongly. U phi of n, a subsequence, will converge to some u in L2 log. And with such convergence, you can pass to the limit in the weak formulation. Okay, so you can pass to the limit. You can send, sorry, this is u, okay, u and j. So you can send nj or j to infinity in the weak formulation. To conclude that U is a solution.